So thanks for joining us today for today's webinar on power factor correction. My name's Ray and I'm the marketing specialist here at Control Logic. I'll be assisting Tennent, one of our application engineers, who will be your host this afternoon. Before we begin, I'll quickly explain how the webinar has been set up. Hopefully now that you all can see the PowerPoint slides on your screen. If you happen to have a question during the presentation, we encourage you to use the Q&A window. Simply type your question in and we'll answer them at the end of the webinar. So to find this window, it's on your top right screen. Or you may find the Q&A tab at the top of your screen, which is the top right of your screen there. If you're using a mobile device, then the Q&A window should be on your main screen. Okay, so if at any stage you're having trouble connecting today, we will be providing a recording of this presentation later this week. Don't forget that we are here to learn, so we're all happy to answer any question you may have. Today we've estimated a time of about 30 minutes. Now I'll pass you over to our application engineer, Tennent, to talk you through it.
Well, thank you, Gray, and good afternoon, everybody. So obviously the topic this afternoon is power factor correction. So you can see up on your slide what we're going to be covering today. So we'll start off looking at what is power factor correction, go through a bit of an explanation on how it works. We'll look at some of the things you need to consider. We'll also do our actual savings calculation example and look at funding models. Okay, so what is power factor? Basically, it's a measurement of how effectively electrical power is being used. Obviously, the higher the power factor, the more efficient the plant is, and this extends all the way back to the generator. Energex, for those of you that don't know, they're the energy generator in South East Queensland. And they have a very good definition up on their website of what power factor is. And basically, their definition is power factor is a measurement of how effectively incoming power is being used as a site. It's expressed as a numerical value between 0 and 1. The closer a power factor is to 1, the more efficient a business is consuming electricity. They also state a power factor between 0.95 and 1 is more cost effective. Okay, so that's just a basic definition on what is power factor. So for those of you that are tuning in today that maybe don't necessarily have an electrical background, the beer glass is a very commonly used way of illustrating power factor correction for those of you that don't have an electrical background. So if we look at the glass of beer shown up on the slide here, you can think about the overall glass as the apparent power. In electrical terms, apparent power is measured in kVA. If we look at the glass, though, there's two components that make up that apparent power. You've got your active power, which is the beer. Okay, so that's the useful power. It's the power it's the reason why you have a glass of beer. Obviously, not only for the taste, but it provides useful power. Okay, electrically, we'll talk about the active and useful power in kilowatts. The other component of the glass is the froth at the top. This is the unwanted portion, or you can think about that in electrical terms as reactive power expressed in kilobars. So depending on what angle the bar staff hold the glass at when they pour you your glass of beer, will depend whether you've got a lot of active power or also quite a bit of reactive power. So you can think about a poor power factor as like holding that glass at poor angle when you pour the beer. So your power factor, now we'll move across to electrical terms. We talk about the active power expressed in kilowatts. You divide that by the apparent power measured in kVA, and that gives you your power factor. Or back to the beer glass analogy, drinkable beer divided by the full glass of beer equals your power factor. Shorthand notation, power factor PF equals kilowatts divided by kVA. So hopefully for those of you that don't have an electrical background, this beer glass analogy will help you to understand a bit more about what is power factor. Okay, so now transferring across to more an industrial site here. So you can see this, what was showing up on the slide in a typical industrial plant. So to the right, you've got an MCC, a motor control centre. And from it, power is being supplied to a couple of AC induction motors. You can see the power is made up of two components. We've got the blue portion of the MCC is the useful power in kilowatts. The top half of the MCC, shown in red, is the reactive power. Now, devices such as induction motors, they invariably consume reactive power. They need this power to create the magnetic fields in their windings for the motor to function correctly. So reactive power is always part of an induction motor that's required to correctly magnetise it so it can operate correctly. Okay, so what causes poor power factor? Well, basically it's inductive loads. So we think about some of the different types of loads there are. Obviously you've got purely resistive loads. With a purely resistive load, the voltage and current are in phase with one another. But when you have an inductive load, an example being the AC induction motor shown on the previous slide, or other examples such as air conditioners, arc welders, these are inductive loads. And with an inductive load, the current lags behind the voltage. And that's what's causing this poor power factor. So if you think about it, you've got a purely resistive load, your voltage and current would be 100% in phase, and you would have a unity power factor of 1. But when you have an inductive load, your current lags behind your voltage, and hence you no longer have a unity power factor. Okay, so we've got a graph, the next graph up here. There's two parts to it. The top part is showing voltage in green, red in current. And this is, say, for an inductive load without any power factor correction. So we can see the current, shown in red, is lagging behind the voltage. And the difference between the current and voltage, shaded in blue, is wastage, it's power that's not being wasted due to this poor power factor. If we now install some power factor correction, we look at the bottom half of the graph here, we can see there's still a bit of a lag between the current and the voltage, but the angle has greatly been reduced. And consequently, the wasted power, shaded bit in blue, is also reduced by improving the power factor. Okay, so just moving away from graphs into more of a real-life example again. On the slide here, to the left-hand side, you've got a supply, so a transformer connected up to the grid, and then we've got a couple of motors, and there's no power factor correction on the left-hand side. So what we can actually see that's being pulled through the supply is both kilowatts, shown in blue, but also this reactive power, which I mentioned is necessary for induction motors to be able to magnetise their windings for correct operation. If we now, moving over to the right-hand side of the slide, install a power factor correction unit. Well, these induction motors still consume reactive power as necessary. However, instead of importing this reactive power through your supply authority transformer, you're producing the required reactive power locally through the PFC unit. So we can now see that only kilowatts in blue is being pulled through the supply authority transformer. And as a result, we've freed up some capacity in that transformer that's shown in that green shaded area. Okay, so now let's just go a little bit more depth about how an actual power factor correction unit works. Well, I mentioned when you've got inductive loads, the current lags behind the voltage. So the way to compensate for that is if you've actually introduced some capacitance into the circuit, this could help correct it. Because when you have a purely capacitive load, your current actually leads your voltage, whereby an inductive load, current is lagging behind voltage. So if you apply a set amount of capacitance to counteract the inductance, you will improve your power factor. So what this slide shows here is a power factor correction unit cabinet with the doors taken off so you can see the different sides. What you'll be able to see, there's different size power factor correction units here. You can see going from left to right, you've got a single tier, a double tier, or a triple tier. Each of these tiers, they have trays, okay, or steps as they're otherwise known. What you have on each tray or step is basically a contactor, you have fuses, you have a reactor, you have capacitors, and some discharge resistors. What's not shown in this slide, particularly on the front of the cabinet door, is the power factor controller. This is a HMI interface, basically, and it's the brains, it's the intelligence of the unit. So what we have here is you have to install a CT, a current transformer, and you typically install that on red phase on your supply network. That's wired back into the PFC unit, back to this HMI controller. Also, you have obviously all three phases of the network connected to the PFC unit. It sits in parallel, okay? And internally, two of the three phases are wired up to the power factor controller HMI. So the HMI basically knows what the power factor is, because it knows voltage and it knows current. It also knows what the load is on the network. The user, when they commission this unit, they enter a number of settings, but one of the key ones is the target power factor, i.e. to what point you want to improve your power factor. Is that 0.95, 0.98, for example? These are user adjustable settings. So the power factor correction unit then knows, right, this is my current power factor, this is my load, this is my target power factor. It then calculates which of these trays or steps it needs to pull in. It could just simply pull in one tray, or it may need sufficient more capacity, it has to pull in multiple trays. And these trays don't necessarily all have to be the same power rating. You can have 12.5 kVAR, 25 or 50 kVAR steps in the ABB range. So the power factor controller will work out how many trays to pull in. The way it does that, it simply energizes a relay output or relay outputs on the controller. These in turn are wired to the coil of the contactors, and it energizes the appropriate contactors, thereby putting that particular tray or step into the circuit. So that's basically how the power factor controller works. So we're just moving forward. So to size up a power factor correction unit, what information do we need to know? Well, we need to know what is the existing power factor. We need to know the target power factor. Generally, a target power factor, as I spoke about at the beginning, referring to the Energex website, they've stated a power factor between 0.95 and 1 is most cost effective. I wouldn't imagine that's going to change much from supply authority to supply authority, but of course, if in doubt, you can check with that, your energy retailer. We also need to know the peak demand, how big is the demand on the network. So the demand could be expressed in amps, it could be in kilowatts, it could be in kVA. Any of those variables are suitable to work out the peak demand. Generally speaking, in terms of what is the existing power factor, quite often a lot of the electricity bills now will have power factor stated on them. However, if they don't, that they do express both your peak demand in kilowatts and your peak demand in kVA. As we saw earlier, power factor is equal to kilowatts divided by kVA. Okay, so it doesn't state your power factor on your electricity bill, but it does state those two variables. We can calculate it. Otherwise, if that information is missing, you can ask, of course, your energy retailer for that information. You may, of course, have some smart metering already on your site that will give you that information. Or if none of those are options, we can also assist you with obtaining this information. But these are the three variables, the basic three variables that are required to size up a power factor correction unit. Okay, so what are some of the things that you should consider before installing a power factor correction unit? Well, the first point is harmonics. Now, for those of you that don't know, harmonics are a form of electrical pollution. They're caused by devices called non-linear loads. A good example of a non-linear load is a variable speed drive. So what happens with a non-linear load, when you apply a sinusoidal voltage waveform to it, the resultant current is no longer a pure sine wave. Instead, it's actually it's a distorted sine wave, and it's basically made up of integer multiples of the fundamental current. So the fundamental current's 50 hertz, but basically you'll get currents flowing that are integer multiples, like the fifth harmonic is 5 times 50 hertz, so 250 hertz. Collectively, these harmonic currents playing at different frequencies add together, and the resultant waveform is no longer a sine wave. Why is this an issue? Well, basically, you get, as you say, you get currents flowing at different frequencies. These can actually flow into the capacitors on the power factor correction unit, and over a period of time, they'll actually cause the capacitors to degrade, and you won't get the expected lifetime out of the capacitors in your power factor correction unit. So, if your total harmonic voltage distortion exceeds 8% on your network, it's not recommended installing a power factor correction unit. Instead, you need to fix up the problem that's causing these harmonics. It could be you might have to install an active harmonic filter, or if the harmonics are confined just to a couple of pieces of equipment, say a couple of large variable speed drives, you might look at other options like installing passive filters specifically for those devices. Again, if you don't know what your voltage distortion is, we may have some smart metering on site, but if you don't, please contact us and we can help you obtain that information. So harmonics is one of the things to consider. Phase imbalance is another. So if your three phases are not that well balanced, when I say not that well balanced, I'm meaning there's a difference of more than plus or minus 5% between phases, you've got to look at fixing up that. The reason being is the power factor correction unit is actually a three-phase unit. So when it's correcting power factor, it's applying the same amount of correction to all three phases. So if your phases are quite imbalanced, more than or less than plus minus 5%, the result by adding power to power factor correction in, you could send one of those phases leading, for example, which obviously you don't want to do. Phase imbalance of greater than plus minus 5% would not be that typical on industrial sites, because industrial sites, the majority of loads would be three-phase. However, if you're looking at putting power factor correction in, say at a hotel, or at a hospital, or in a commercial building, those type of sites will have a lot more single-phase loads, and it'd be virtually impossible to evenly distribute all these single-phase loads across all three phases. So invariably, you're going to get some phase imbalance. So though it's a possibility at an industrial site, it's far more likely to have this larger phase imbalance at commercial sites. Again, if you've got smart metering, it should show the balance. It'll show each phase individually, so you can see the balance. But again, if you can't, you're not able to obtain that information for yourself, please contact us and we can assist you. The next requirement is cooling requirements. So power factor correction, it's electronic device, basically the controller, and heat is the killer of electronics. So if the ambient temperature on the site is greater than 45 degrees, you'd want to look at some other options, maybe installing air conditioning, that type of thing, to get the ambient temperature down below 45 degrees C. The final thing you need, of course, is a current transformer. This doesn't come with the PFC unit standard. When we supply a PFC unit, we'll always offer a CT to go with it. As I mentioned previously, the CT is typically located on red phase. So for us to be able to supply you a CT, we would need to know the current rating of the bus bar or cable the CT is going to go on, the physical size, so we can make sure the aperture, the opening of the CT is large enough, and then we can supply you with a current transformer as well. Okay, so we've looked at what is power factor correction. We've described how it works, and we now need to look at some of the benefits or reasons of why you might want to install power factor correction. What's in it for you? Well, many of the energy suppliers have now moved to KVA-based tariffs, or if they haven't already done so, they're in the process of doing so. For example, Energex, who are the energy generator in South East Queensland, they moved to a KVA-based tariff as of the 1st of July 2015. Now, it's not for all customers, it is for people with a certain annual usage. And the figure Energex is working on is 100 megawatt hours per annum. So if your plant is using more than 100 megawatt hours per annum, then you would, you're in South East Queensland with Energex, you would be on a KVA-based tariff. So previously, before the KVA-based tariff, Energex only charged you for your kilowatts, the useful power. But you may have had a poor power factor, and Energex would have had to supply you with reactive power as well. But they only ever charged you for the kilowatts. So now by moving to the KVA-based tariff, you're getting charged for both your kilowatts and your kilobars, which collectively is your KVA So it's a way Energex can help cover the cost of having to supply that reactive power to your site so they can build their infrastructure to cater for it. So if you look at on the slide here, it may be a little bit hard to see, but there is an element on the electricity bill called the critical demand component, and that is charged in dollars per kVA per annum. A little later in the presentation, I'll go through a practical example of how you can calculate your electricity bill savings by installing power factor correction. So one of the main reasons that people look at power factor correction is they're on a kVA-based tariff and they're getting penalised for a poor power factor. Okay, so the next reason for improving power factor. Well, basically freeing up capacity. So what we see here on this slide here is a transformer. It's a 1500 kVA rated transformer. And what we can see is basically the power factor has been improved up to 0.9. By improving the power factor to 0.9, the kilowatts have been reduced, and consequently the kVA has been reduced. They've been able to recover 22% capacity. So you think about it, your main incoming transformer, it might be quite close to full capacity. Okay, you want to add on another machine or even another production line. Okay, this may actually mean you won't have enough capacity in the existing transformer. So you've got two choices. Obviously, choice one is to upgrade your transformer. Well, that's going to be very expensive. I mean, not only is it the cost of the transformer, but there's all the installation costs involved with it and production downtime. So if you're close to capacity on your transformer and you want to expand and you happen to have a poor power factor, one way around that, of course, is installing a power factor correction unit on your site, reducing the reactive power locally, and therefore you're not importing the power and you're recovering capacity on your transformer. So that's another reason people consider installing power factor correction. And the third point is extending equipment lifetime. So if you think about it, you've got lots of reactive power flowing, obviously extra currents are flowing through, currents having a heating effect on cables, bus bars, transformers, motors, all that type of thing. So obviously by reducing the amount of current and reducing the heat, it stands to reason that you're going to help improve the longevity of your equipment. Okay, so I mentioned three key reasons why you might want to look at installing the power factor correction. And now I'd like to just give a practical example. So the scenario is, we've got a customer, their existing power factor is 0.73. So it's not particularly good. I've seen worse, but it's certainly not a good power factor. They have a peak demand of 500 kVA, and they get a demand charge of $18.75 per kVA. So how much will they save per month if they improve their power factor from 0.73 up to 0.95? So step number one, we need to calculate the kilowatts. So the kilowatts already seen is equal to the kVA, which is in this case is 500 times by the power factor, which in this case is 0.73. So the result of kilowatts is 365. The kilowatts is not going to change when we improve the power factor because it's already the in-phase component of voltage and current. So having calculated the kilowatts, our next step is to calculate the new kVA. So what we do is we take the kilowatts, which we calculate in step one, being 365, we divide that by our new target power factor of 0.95. Straight away, based on improving the power factor of 0.95, the kVA is reduced from 500 down to 384. So the final step is simply subtracting the existing kVA, new kVA away from the existing kVA. We see we've got a kVA reduction of 116. Customers getting charged $18.75 per kVA, so multiply 116 by the per kVA amount, and you've got a saving of $2,175 per month. Multiply that by 12, you're up over 25,000. Now it depends, of course, on the size of power factor correction unit you've had to install and the installation costs, which can be site specific. But for a power factor correction unit of capacity to achieve this on a 500 kVA peak demand and a 0.73 power factor, you'd be looking at a return on investment of approximately around about the 12-month mark. So after that, you're saving $2,175 per month. So what we'll look at on this slide here is a couple of funding models. There's a managed service agreement that ControlLogic can provide, or there's a traditional straight up front purchase of the PSC unit. So obviously, if you look at we'll go through them, if you look at the initial cost, well, under a managed service agreement, there's $0 up front, whereby obviously if you're going to purchase the unit outright, you've got to make an upfront payment. So it may be that you want to you can see a business case for installing power factor correction unit on your site. However, you don't have the capital expenditure available at this point in time. So then under that scenario, a managed service agreement could be a really good option for you. Straight away, you're able to save money on the electricity bill, but you can pay for it, make monthly payments for the managed service agreement out of operational expenditure. Of course, if you purchase outright, then you've got no ongoing payments. Okay, warranty. With the ABB power factor correction units, the standard warranty is 1 year. However, ControlLogic is an authorised service provider, supplier of ABB power factor correction, and have attended service and maintenance training courses. And we're therefore authorised to carry out servicing of the ABB PSC units. And what ABB have said is that if we get the unit serviced each year, we keep records of that, the warranty will be extended from 1 to 5 years. So we can offer you a 5-year warranty. We obviously, as part of that, would come on and organise for the unit to be serviced once a year. So out of the managed service agreement, that servicing cost will automatically be built into your monthly payments, whereby if you purchase up front, obviously at the time of quoting you the unit, we can offer you the yearly service fee if you would like to extend the warranty from 1 to 5 years. Managed service agreement, obviously 5 years maintenance and service schedule, as just mentioned. The purchase outright, your payback period, depending on the size of the unit and the installation costs, anywhere from 1 up to 3 years. So there's a couple of funding models, and as I say, you can see a need for it on your site, but you don't have the capital expenditure. Please talk to us about a managed service agreement. I'd also like to take this opportunity to, if you've got any applications at this point in time, to contact us for a free energy feasibility assessment. What we need initially is for you to send through a copy of the electricity bill. You can obviously mask out any confidential information, but if we can look at the electricity bill as a starting point, we'll then let you know if we need any additional information in order to quote you a unit. Well, that concludes the formal part of the presentation. I'd now like to throw the floor open for any questions.
Thanks, Pete. Okay, so if you do have a question, please feel free to start typing a question into the Q&A section. We do have a few questions here already though, Pete. So the first one we have here is basically how much does power factor equipment cost?
That's a good question. I don't want to give a politician's answer either. Actually, there's a very varied range in power factor correction sizes, so they can go anywhere from the smallest would be 25 kilobars, okay, all the way up to in excess of 800. So the dollar value can vary widely, you know, from $3,000 to $4,000, for example, all the way up to 15 to 20,000. So it's very varied because there's so many different size units and so many different applications. But there's a broad brush anywhere from say 3,000 up to 20,000.
Is it possible to achieve a power factor of 1?
Well, yes, in theory, it's possible to achieve a unity power factor. Whether it's cost effective is another question, because it's not a simple sort of linear relationship of, you can say going to 0.9 from 0.95 up to 1, i.e. you don't just simply add, 50 kilobars to go from 0.95 to 0.96 and so on. The closer you get into unity, the more resources it consumes. But yes, it is possible to achieve a unity power factor, but in many cases it probably wouldn't be cost effective to go to that extreme.
Okay, there's a question here asking why don't we want a leading power factor?
Well, if you actually had a leading power factor, you would actually be exporting power. You'd be putting power back onto the onto the network, which the supply authorities wouldn't like.
Okay, so also what type of maintenance is required for the power factor correction hardware?
Yeah, so basically once a year we carry out a maintenance of the unit. So that would range from all your basic, standard electrical checks, making sure all connections are tight, nothing has worked loose. Cooling is a big part of the power factor correction, as I mentioned, obviously, as any electronic device. The cooler you keep it, the more longevity you get. The power factor correction unit cabinets have obviously inlet filters and cooling fans. So other things we're obviously doing here is checking the filter mesh, replacing that if it's become clogged and impeding airflow. Obviously making sure the fan is working correctly. Other things we'll be checking for as well is harmonics. So I mentioned about before installing the power factor correction unit to make sure the harmonics don't exceed total harmonic voltage distortion of 8%. However, it could be during that year another piece of equipment to come onto the site that has a large variable speed drive. Suddenly your harmonic levels, which were fine previously, have now increased. So that's another thing we check. And finally, making checks on the capacitors as well to make sure they're still within certain tolerances. So they're the main checks we would do at a yearly service. Okay,
so this question here is saying, depending on the installation, obviously cooling will be an issue. So is it possible to incorporate like another product such as Tennent as a standalone product?
Yeah, that's absolutely right. I mean, ControlLogic have a range of thermal management solutions. So it might be that, for example, if you're going to put it in a switch room, you might need to look at installing an air conditioning unit, for example. Or we have other cooling, thermal management products, and we can assist with that also.
What's the effect of going power factor from lagging to lead when power factor correction is used?
Well, you don't want the unit won't set the power factor leading, assuming that you haven't got phase imbalance of greater than plus minus 5%. So the power factor correction unit won't allow so many trays or steps to be pulled in as to send the power factor leading, because at that point then you'll be starting to export your power, and the PFC unit won't allow that to happen.
Okay. There is a question here asking really what is bad power factor? What is bad power factor?
Well, bad power factor, as mentioned, is where your current is lagging behind your voltage, and you're wasting a lot of power. You're not using the power efficiently. As I mentioned, it's a numerical value. So if you did have a unit of power factor, so voltage and current are 100% in space, you'd have a power factor of 1. The worse the power factor gets, the worse the number gets. So if you had a power factor of less than 0.9, I would consider something of 0.9 or below, where you might want to start considering power factor correction as an option.
Okay, so there's an extension to that question. Is it below 0.8 or 0.9?
Well, yeah, basically, I would suggest if you're 0.9 or below that point, you really want to start considering power factor. That would be where I would be starting to give it serious consideration below 0.9.
So what changes need to be made then on existing switchboards to incorporate power factor correction?
Well, the power factor correction units we've installed, there's a couple of options. We have a complete freestanding cabinet, ABB manufactured complete cabinets. Depending on the size, they'll either be freestanding or the smaller ones that are wall mounted. So if that's the case, you really only need to have, obviously, physical space for this new cabinet to go in your switch room. You also need to look at when you're going to do isolation actually at the cabinet or the existing switchboard. You'll have to run cables from the existing switchboard to the PFC unit. So it's basically, do you have sufficient space, and is it practically easy to be able to connect in electrically and install the power factor correction unit, which sits in parallel. The other option is we can supply the power factor correction unit as loose components. What I mean by loose components, there will be those trays or steps and the HMI controller, and you build them into your own cabinets.
Okay. Does the power factor correction unit have data networking capability, and can they be controlled?
That's a very good question. There's two HMI controllers with the ABB power factor correction units. There's the more basic one, the RBC, and then there's the more advanced RBT, the RBT being a colour touch screen. The RBT supports the option for a comms module, a Modbus RTU comms module, and there is on a certain version as well an Ethernet option. I'm pretty sure, I'll have to double check and get back to you, but I'm pretty sure obviously you can read everything, and I'm pretty sure being Modbus, you can write to certain parameters as well.
Okay, cool. So there's a question here asking, as an electrical contractor, are there any training opportunities to develop my business into this field?
Sorry, are there any
training opportunities?
Yes, we can assist with training. If that's something that interests you, which obviously it is, I might get you just to send us an email with your details and go into it more specifics. But the short answer is yes. Every regular intervals, ABB do host, offer a service installation and service course, so we can arrange for you to attend one of these and become an accredited PFC installer. But we can talk about that in a bit more detail, so I'll get you to shoot us an email with that.
Okay, so there's a question here about cost again. How much is the yearly service?
Yearly service, if you're purchasing it up front and doing the individual yearly service, it's a little bit of a hard one to answer, because obviously it depends where the site is and travel time. But roughly speaking, for 4 hours, so let's say an hour for travel, average way for travel, 2 hours on the site, might be up around about the $600–700 mark.
Okay. So how do you size up the PG correctly?
For the current transformer, basically it's actually going to sit on the main bus. Okay. So, for example, if the main bus is supply network where you're trying to correct the power factor correction unit on, say had a load of 1200 amps, you'd obviously need to get a CT with at least a 1200 to 5 ratio. So obviously the current rating of the CT has got to be greater than or equal to the current rating of the bus or cable that it's going to be located on. And obviously we just want to double check as well the physical size of the bus bar to make sure the CT aperture is sufficient to go over that bus bar. The CT should have a recommended a class 1 accuracy, so it gives a decent resolution back to the PFC controller to be able to get accurate information of the network.
This question here is asking what brand we use for the power factor correction.
So we're an authorised partner of ABB Power Factor Correction, so that's the brand we sell.
How much physical space does a power factor correction unit occupy for a 35 kVA and 800 kVA unit?
Very good question. For the 35 kVA one, we would have would be a 2-step unit, a 25 and a 12.5, would be 37.5 kilowatts, and that would be a wall-mounted unit. From memory, off the top of my head, it's 600 wide by 1200 high. I think from memory though, there's a 100% hole to it. I think it's about 300 or 400 mil deep for a wall mount one, so that's for 2 trays, a 25 and a 12.5. An 800 kW would obviously be a big freestanding cabinet. You would be, you'd have 3 tiers. So each tier is 600 wide, so approximately 1800 long, I think 600 deep, depending on the IP rating, top or bottom entry, you're around about 2200 high. So approximately 800 wide by 2200 high by 600 deep.
If you installed a large solar system, would that reduce the power factor?
Well, introducing the solar system, it wouldn't change your power factor at all. Obviously, it means by having the solar, you're importing less power from Energetic or from whoever your electricity supplier is. You're importing less power. So if you've got a poor power factor, you'd be producing more of your power locally. So it would help bring down your peak demand, but it wouldn't obviously do anything in its own right to correct power factor.
Speaking of ABB power factor correction unit, will that monitor harmonics as they become present?
Yes, it does. The RVT controllers, they monitor harmonics, and they generate alarms, and they can also be programmed to actually disconnect the trays, the steps, if the harmonics exceeds a certain limit to protect the capacitors.
Okay, I have a final question here. So what's the benefit of a thyristor PFC unit compared to the capacitor system?
Good question. Okay, I think there's probably a couple of points going on there. The ones I've been speaking about obviously have the capacitors and they have the contactors to pull in and out those trays. ABB do have another unit called Dynacop, and instead of using contactors to energise or de-energise the capacitors, it uses thyristors. The advantage of that is switching things out much more quickly, and you can compensate for loads changing or very dynamically changing loads. It's very fast reacting compared to contactors and waiting for discharge times. So I'm not 100% sure I've answered your question. There is a third permutation, and that's an active harmonic filter, but that can not only that uses IGBTs basically. It not only can correct harmonics, but it can also correct power factor correction. But that comes at a price, so that obviously it's a lot more expensive than the power factor correction unit. So you wouldn't use it if your sole purpose is to correct power factor. You'd be using it if you're trying to kill two birds with one stone, i.e. help reduce harmonics and improve your power factor. So hopefully that's answered your question, but if it's not, if I haven't, please shoot me an email and we can further discuss.
Okay, so if there are no more questions, I just want to thank everyone for your attendance today. We hope you gained something valuable from it. Now, we know there was a lot to take in today, so if you happen to think of a question we may not have covered, you can feel free to send us an email or give us a call. So don't worry, also, if you've missed something today, we're providing a recording of this event. So please check your email in the next few days for this. So I guess that concludes the webinar today. So until then, we hope to see you next time. Thanks, everyone.